Anyway, please, Anna Balibanu is our next speaker, and she will speak about moment maps, multiplicative reduction, and Dirac geometry. Thank you.
Yeah, thank you, and thank you to the organizers for the invitation to speak. So I want to begin by giving you some motivation for the content of this talk through examples of reduction type procedures in Poisson geometry that are familiar to us from representation theory. So let me just do some setup. So I'm going to begin with a Poisson manifold. What do I mean by a Poisson manifold? I mean a manifold equipped with a bivector that induces a Poisson bracket, so such that bracket on functions defined by f bracket g equals pi applied to the differential of f. Differential of g satisfies the Jacobi identity. So the Jacobiator f bracket g bracket h plus cyclic permutations is equal to 0. And whenever I have such a manifold, this bivector pi induces for me a map from the cotangent bundle of M to the tangent bundle of M that just takes a one form and contracts pi with it. So I get a vector field. And the image of this map is a distribution in the tangent bundle, and it's the distribution that integrates to the foliation of M by symplectic leaves. So M is, what do I want to say, foliated by symplectic leaves. So in particular, an example that is central for us is if I take I'll just write Lie group G. What I'm saying right now is true for real Lie groups. For complex Lie groups, for algebraic groups, if I take a Lie group G, then I let fractor G be its Lie algebra, and then the dual of this Lie algebra has the Kirillov constant Poisson structure, whose leaves are exactly the co-adjoint orbits. And the observation that I want to make about this kind of data is that if I have a Poisson map which I will suggestively call mu from M to G star, then this Poisson map induces for me an action, an infinitesimal action of the Lie algebra G on the manifold M. And the way that it does this is it takes an element of the Lie algebra, and I can view this as a one form on the dual of the Lie algebra, and then I pull it back by mu star to get a one form on M, and then I apply this pi sharp map to get a vector field. And this action may or may not integrate to an action of the group, but in general it's a Hamiltonian action. So what you recognize here is exactly the usual moment map condition. So this is, let me write it here. So this is a Hamiltonian action whose moment map is exactly mu. once we have this situation, then we can do what we call Hamiltonian reduction. Which, kind of, in its most pure form, introduced by Marston and Weinstein, looks like I take alpha in G star to be a regular value of mu. And then the fiber of mu above alpha is a submanifold of M, and I can quotient by the action of the centralizer of alpha. And this guy gets a Poisson structure by pulling back from M and then kind of pushing down to the quotient. So for my remaining examples, I'll restrict to the case where G is a complex semi-simple group. And then the second example I want to...
You said that in this example you need that G is semi-simple.
I know. I from now on I will need that G is semi-simple. Yeah. So I'll need the G is semi-simple, and then I'll kind of freely identify G with G star using the killing form. And then example 2 that I want to talk about is what people call Whittaker reduction. Which is reduction that happens using Slotoway slices. So I begin with an SL2 triple EHF in G, and then I take
Would you say just in example 1, so when you're saying mu inverse alpha mod G alpha, you're saying that even if you just have the Lie algebra, you can just
yes.
that big invariant things.
Yes. So in the talk today, everything will integrate to the action of the group, but I mean in general, you could also just mod out by like the distribution induced by this infinitesimal action. Yes, I could have fractor G's everywhere. So I get from any SL2 triple a Slotoway slice, which is F plus the annihilator of E. And in the very nice talk on Tuesday, we learned that by work of Ginsburg and Gann, there's a unipotent subgroup U of G that gives us this kind of transversality theorem that says that if I apply the adjoint action of U to the Slotoway slice, I land in F plus the annihilator of the Lie algebra of U, and that this action map is actually an isomorphism. So using this result, I can do Whittaker reduction. There are kind of two choices for how to do it. I can take, so I have my moment map mu that goes from M to G star, but now I think of G star as just being identified with G. And inside G I have the Slotoway slice. Preimage of that lives in the preimage of F plus mu first. And these are both submanifolds of M. And I can quotient by the action of this unipotent group U. Here I'm going to have an isomorphism. And by just a kind of variant of usual Hamiltonian reduction, I get a Poisson structure on this quotient. So if M, the manifold, is just equal to G, then this is the usual Poisson structure produced by Gann and Ginsburg on Slotoway slices. And another observation is that in this example, I don't actually need any regularity assumptions to get something smooth, because these Slotoway slices are always transverse to the adjoint orbits. So this means that they're transverse to this moment map. So when I pull back, I always get a smooth manifold. So this was example 2, which, like I said, can be kind of cooked up out of example 1 by reducing with respect to the action of the subgroup U. So this is actually just a variant of normal Hamiltonian reduction. Example 3 is a bit more high tech. So I call it the more Tachikawa spaces. So these were introduced by Ginsburg. Sorry?
And not more in Tachikawa.
Well, I mean, but they were introduced by Ginsburg and Kazhdan as this kind of conjectural solution to a TQFT conjectured by Moore and Tachikawa. So this, I think, this is what people call them. So in this example, we take our SL2 triple to be regular, and in this case, we get this spot-away slice S, which is sometimes called the principal slice. And then make some definitions so that here we'll define the universal centralizer. This is the group scheme consisting of pairs A in the group and C in the principal slice with the property that A centralizes C. So this is like the family of centralizers of points in the principal slice, and the principal slice is like a cross section to the regular adjoint orbits. So because each centralizer fiber in the group scheme is the centralizer of a regular element, it's an abelian group. So this is an abelian group scheme. And because it's an abelian group scheme, I can consider the kind of n-fold multiplication map of C, and this is a group scheme homomorphism, which means that when I take its kernel, I get another group scheme over S, and I'll call this guy H. So this is a group scheme over S. And what Ginsburg and Kazhdan proved is that if I look at the cotangent bundle of the product of n copies of the group, this has two actions of g to the n, one coming from left multiplication and one coming from right multiplication. So its moment map is going to land in g to the n cross g to the n. And inside here, I can take the submanifold consisting of everything in the first coordinate and just the diagonal copy of S in the second coordinate. And in this case, H acts on the preimage of the subspace. And when I take the quotient, by this action, well, this is symplectic. And in fact, it's more than that because it has a residual action of g to the n coming from the side that I didn't mod out by. So this is the same thing as saying that it has a Poisson map to Lie algebra g to the n. So this is actually a symplectic Hamiltonian Gn space.
Is it related to equivariance Lodovi-Slice, this construction?
Is it? I don't know the answer to this. But there are people who are much more expert on these varieties here than I am, so maybe we can ask one of them. The thing that I want to point out is that this third example is no longer, it doesn't fall under the umbrella of like usual reduction anymore, because now what's happening is that the reduction is by the action of a group scheme and no longer by the action of a group. So this is, there's more to prove than just an usual Marsden-Weinstein reduction. And my goal in this talk is to explain some multiplicative analogs of these examples. And then maybe, if time, also say a bit about how to prove this. But before I do that, I have to say what I mean by multiplicative analog. So what I mean is that I want to give some kind of framework for Whittaker reduction, or for reductions like the one that appears in these more Tachikawa spaces, when our usual Poisson manifolds and kind of Lie algebra valued moment maps are replaced by group valued moment maps. And to say what that means, I'll give a quick recap of what are called quasi-Poisson manifolds.
So, sorry, on the bottom board here,
Mhm.
it's supposed to be mu inverse of f plus mu, no, the other one, mu, and the bottom, isn't it f plus u?
Yes, sorry. Thank you. Any more questions?
This group scheme, is it reduced or?
Mm-hmm. Yes. Actually, this group scheme itself is a symplectic variety, and is a Whittaker reduction of the cotangent bundle of G. Sort of incidental. Okay, so what is a quasi-Poisson manifold? To define it, we need to notice that the Lie algebra G carries something called a Cartan 3 form. So this is an element of wedge cubed of G star, which is defined by taking the algebra elements x, y, and z, and taking the killing form of x with the Lie bracket of y and z. And then because I can identify G and G star, what I get is something called the Cartan 3 tensor, just the image of this guy under that identification, which is an element in wedge cubed of G. And then if I have an action of my group G on a manifold, this gives me an infinitesimal action of the Lie algebra. So this is a map that takes Lie algebra element xc to some vector field xc sub m. And this map takes this Cartan 3 tensor to a trivector field on the manifold M. And now I can give a definition, a quasi-Poisson structure on M is a bivector pi, so a section of wedge squared Tm, that has the property, do I want to say? That has the property that the induced bracket satisfies like a kind of twisted version of the Jacobi identity. So instead of this Jacobiator being equal to 0, it's going to be equal to this chi m applied to the differential of F, G, and H. So what you can think of is that if I view like the Jacobiator as just something that eats kind of three differentials and spits out a constant, then it's a trivector field. And the statement is that this Jacobiator of pi is exactly the trivector field induced by this Cartan 3 tensor. And there's a notion of what it means for such a bivector to be Hamiltonian. And this is if there's a group-valued moment map. Mu. So now I take the values in G, and this satisfies a condition that's kind of analogous to the usual moment map condition, but which I decided I wouldn't write down because we're not going to use that. So these guys are kind of multiplicative analogs of Poisson manifolds, and they have the property, if they're Hamiltonian, that they also have a foliation by submanifolds that carry two forms. And these two forms are no longer symplectic, they're what's called quasi-Hamiltonian. So quasi-Hamiltonian leaves. In other words, M is going to be a disjoint union of leaves of the form L omega, but now omega is a potentially degenerate, non-closed two form. And its differential is minus the pullback of the three form eta through the moment map mu.
So if you just have a quasi-Poisson structure itself, it's not Hamiltonian, then you still have this. You don't need to have a group. Right?
You don't.
Quasi-Hamiltonian leaves. You don't need to have a group value.
No, you do actually.
Oh, you do.
Yeah, I think there are examples. I wouldn't be able to give you one off the top of my head, but somehow for this.
Leaves are with respect to the group action.
Yes.
You get the trivial group, and you get the trivial, just the points or something.
If you take the trivial group, then a quasi-Poisson structure is just a Poisson structure, and then you're symplectic.
Hamiltonian leaves.
But in general, somehow the way that these things are proved and defined really depends on this moment map in some kind of essential way. So I don't know. I've never seen anything about non-Hamiltonian quasi-Poisson. Because somehow the group action is already baked into the definition of quasi-Poisson. So it's,
Oh, I see.
you know, because this trivector field really comes from the group action. So then it's kind of weird if they're not actually Hamiltonian. It's not a.
I see. Yeah, you need to have a group action anyway to be quasi-Poisson.
So let me give a first example where M is just the group G. So M is G, and it's being acted on by itself via the conjugation action. So this group has a natural quasi-Poisson structure. Which we can write a formula for. That's the sum of EIL with EIR. So these are left and right invariant vector fields, and the EIs are an orthonormal basis of the Lie algebra G with respect to the killing form. And the quasi-Hamiltonian leaves of the structure are exactly the conjugacy classes. So So we should think of this example as a multiplicative analog of the Kirillov constant Poisson structure on the Lie algebra G. Where now the foliation, which was previously given by adjoint orbits, is given by conjugates and glosses.
Wait, so these quasi-Hamiltonian leaves, they're still not.
They're not symplectic.
They're not
The form is not closed, and it's there are many points where it's also degenerate.
And similarly, in the G case, where in G should I expect it to actually be symplectic?
Where at points G, so that add G doesn't have a -1 eigenspace. Okay, so second example. I will look at a product of two copies of the group acting on the space D sub G, which is sometimes called the internal fusion double, which is also a product of two copies of the group. But this action, what does this action look like? I'll write it here. This action looks like G comma H applied to a point A comma B is equal to G A H inverse H B H inverse. So this has a quasi-Poisson bivector for which I won't write down the formula, and a moment map.
So G doesn't act on the second.
Yes, I will say in a second why this is not surprising. So the moment map that takes a point A B to A B A inverse comma B. So this is quasi-Poisson. It's actually quasi-Hamiltonian, so it only has one leaf. And what you should view this as is a multiplicative analog of the cotangent bundle of the group G. So
Just to make sure I got the terminology here, so you, in order to be quasi-Hamiltonian, you have to be Hamiltonian plus only one quasi-Hamiltonian leaf.
yes, exactly.
Quasi-Hamiltonian is much stronger than Hamiltonian.
It's not clear why these leaves are called quasi. I mean, the reason is that historically the quasi-Hamiltonian two forms were introduced before anyone introduced quasi-Poisson structures, and then they had some inspiration from physics, and then somehow we ended up with this terminology. So maybe they should be called like quasi-symplectic or something, but it's too late to do anything about this. So what you notice here is that this action looks a lot like the two-sided action of the group G on the cotangent bundle of the group G with respect to the left trivialization. And this moment map looks exactly like the moment map once we make that identification. So this is like a groupie analog of the cotangent bundle of G identified with G cross Lie algebra via left trivialization, which is a Poisson manifold with a single symplectic leaf. So in this quasi-Poisson setting, we can also do reduction. We can reduce at a point. If I take a point A in the group G, that is a regular value of the group valued moment map mu, then the fiber of mu over A is a submanifold of M, and I can take the quotient by the centralizer of A, and thus gets an honest Poisson structure. Because I've kind of modded out the symmetries of the group G, so now the only group that's acting is the trivial group. But in general, if we try to use this to do other kinds of reduction, things become much more complicated in the quasi-Poisson setting. For example, it's hard to reduce with respect to the action of a subgroup, because if M is a quasi-Poisson manifold for the action of G, this doesn't necessarily mean that it's a quasi-Poisson manifold for the action of a subgroup of G, because of this the Cartan 3 tensor. So let me restate kind of a broader goal, which is to find a common framework that includes reduction of Poisson manifolds of quasi-Poisson manifolds of potentially of other geometric structures. So this was the purpose of my work with Maxence. Did I say? I didn't say it out loud, but all of this is joint work with my collaborator Maxence Mirand, whose name I did not forget to write on the board. So we did this using some tools in what is called Dirac geometry. But my plan for this talk, because there's a fire alarm that will go off in 20 minutes, is to first tell you the consequences of this goal, and then in the very unlikely event that I have time remaining before the alarm, I will also say a bit about how to prove it. But the consequences are kind of the more representation theoretic part. Any questions? Okay, so the first thing that I want to talk about is the multiplicative version of Whittaker reduction, which I discussed at the beginning of the talk. And Whittaker reduction was kind of taking place along Slotowee slices. And this multiplicative version will take place along a multiplicative analog of Slotowee slices, whose inventor is here in the audience. So I'm a bit shy to talk about them. So W will be my Weil group of G, and then to any element of the Weil group, I associate a preimage in the group that is a normal representative. So here I'm making some choices of maximal torus, of Borel, of a Chevrolet basis, and then a normal representative is a representative of the Weil group element that is kind of compatible with this chosen basis for the Lie algebra. And then using this, I can assign to W a distinguished parabolic subgroup P of with Levy decomposition L times U inside G. And this parabolic has the property that the derived subgroup of the Levy, one way to say it is that its root system is fixed by the action of this Weil group element W. So it resides in the fixed point locus of W on L, which fixed point locus I will call Z. So how to actually construct this parabolic is a bit of a technical explanation, but it leads to the following transversality results, which are due to Sebastianov. So there's associated to W a transversal slice, which I'll call sigma sub W. This is, I forgot something. Once I have this parabolic, I can define the following subgroup U sub W will be the intersection of the unipotent radical of P with the opposite unipotent radical conjugated by W inverse. So now my transversal slice, sigma sub W, will be U sub W Z W inverse. So this is a slice that's transversal to the conjugacy classes of the group G, and it passes through the point W inverse. In the case where W is a Coxeter element, then it has, then it fixes no simple roots, and it also fixes no points in the torus. So the Z factor disappears, and what I recover is the Steinberg cross-section, which is a cross-section to the regular conjugacy classes in G. And so I have this transversal slice, and I have a theorem. What do I want to call it? Maybe a cross-section theorem. That says that when I conjugate this slice by the action of U, I land in the subspace U Z W inverse U. Sub W, and this conjugation map is actually an isomorphism. So what we should be thinking is that sigma is an analog of a Slotoway slice F plus the annihilator of E, and theta is an analog of this F plus U perp. That was the U saturation of the Slotoway slice. So the first observation is that both of these spaces are stable under the conjugation action of Z. Z normalizes U, it normalizes U sub W, and it commutes with the Weil group element representative W. And then I'll state theorem which says let M be a quasi-Poisson G manifold that is Hamiltonian with moment map mu. Then I have a very similar diagram as in the case of Whittaker reduction. So I can take the preimage of sigma sub W under the moment map mu. Again, because sigma is transverse to the conjugacy classes, it's also transverse to this G equivariant map mu. So this is always a smooth submanifold. This lives inside the preimage of the larger space theta, lives inside mu, and I can quotient here by the action of u. So this quotient always exists because it's isomorphic to this space. And this is quasi-Poisson with respect to the residual action of the subgroup C. So in particular, if the manifold M is just the group G itself, then this is a Hamiltonian quasi-Poisson manifold with moment map equal to the identity. And this gives us a quasi-Poisson structure on these transversal slices.
Could you recall which Poisson structure do you use on G?
On G. On G, use the quasi-Poisson structure that is here. Yeah, so everything is quasi-Poisson. It's not entirely clear to me. So there is also a Poisson structure on these slices. It's not entirely clear to me how these two are related. Okay, so this was the first multiplicative analog of Whittaker reduction. And the second one that I want to describe is some kind of multiplicative version of the more Tachikawa spaces. Which now that we have these slices is a pretty naive analog. So in the case where W is a Coxeter element, like I said, my subgroup C becomes trivial, and the slice sigma is just the slice U sub W times W inverse. So this was introduced by Steinberg. And thus this cross section is proved by Steinberg in the special case of this regular slice. So this is a cross section to the regular conjugacy classes in the group C. And I can play with it kind of the same games as I did with the principal Sladowee slice. I can define a multiplicative universal centralizer, which, probably there are too many Z's, which I'll call fancy Z. So this will be pairs A in the group and G in the slice sigma with the property that A centralizes G. And once again, because this universal centralizer is an abelian group scheme, I can, because centralizers of regular elements in the group are also abelian, I can take the kernel of its n-fold multiplication map. And this is going to be an abelian group scheme living over sigma. So with this data, we can do the following reduction. We can look at the internal fusion double It's over here. So in this example, I now replace g by g to the n. This is a groupie analog of the cotangent bundle of g to the n. So it will have a group-valued moment map that lands inside g to the n cross g to the n. And this has sitting inside it as a submanifold the first coordinate times the Steinberg cross-section in the diagonal in the second coordinate. And then what happens is that this group scheme H over G acts on the preimage of G to the n times sigma diagonal. And when I take the quotient, by this action, well, when I take the quotient by this action, just as before, the space is a residual g to the n action coming from the original left action. And a natural map to g to the n coming just from like the first component of this map mu. And this is going to be a quasi-Poisson space with respect to this Gn action. So in these groupie Moitach-Kawal varieties, at every step n, I get a Hamiltonian quasi-Poisson Gn manifold. What time do I have to stop?
You started at 40, so we have until 40.
I have until 40. Okay, so maybe I will talk and then we'll make a break for the fire alarm.
Exactly.
For n equals 2, do you get multiplicative cotangent to dg?
For n equals 2, cotangent to dg. I think the dimensions are a bit off. So for n equals 1, I think I get the universal centralizer. And for n equals 2, I get something that looks like this, which I can also think of as something that looks like this, which is some kind of multiplicative version of the twisted cotangent bundle of G mod U.
And n equals 3?
I don't think anybody knows. So I think even in the additive case for n equals 3, it's cotangent to G. This maybe this is true, and we have to check. Okay. So let me say a little bit about how we prove these results. In fact, our main theorem is kind of, like I said, a more general reduction theorem, and it's happening in this world of Dirac structures, which gives some kind of unified way to think about Poisson things, quasi-Poisson things, twisted Poisson, many different kinds of geometric structures. So in order to define them, I'm going to consider something called a generalized tangent bundle. So I take my manifold M and I take the vector bundle sum of the tangent bundle and the cotangent bundle. So this is a vector bundle over M. And this space has a natural non-degenerate pairing. So if I take X alpha and Y beta, they pair to alpha of Y plus beta of X. And it also has a bracket, which is called the Courant bracket, and a bracket of X alpha with Y beta in the first coordinate is just the usual Lie bracket of vector fields. And in the second coordinate is some more complicated expressions. So I take like the Lie derivative of beta with respect to x minus the contraction with y of d alpha.
That's good timing.
This is not so bad. They have very gentle fire alarms.
And you only tell Leah when it's for real.
Okay, so now I can define. The notion of a Dirac structure. On M, and it's going to be a subbundle L of this generalized tangent bundle that has the property that it's Lagrangian with respect to this non-degenerate pairing. And that it's closed with respect to this bracket. And the observation is that if we restrict this bracket to a Lagrangian subspace of this bundle, then it becomes a Lie bracket. So this is now going to be a vector bundle over M that has a Lie bracket and a natural map to the tangent bundle that respects the brackets, the two bundles. And this is what's called a Lie algebroid. So this implies that L is a Lie algebroid over M. So let me give you some examples of Dirac structures that come from familiar things. So if I start with a symplectic manifold, then I can define L to be the subbundle of pairs of the form x, comma, contraction of omega with x. We should think of this as the graph of omega viewed as a map from the tangent bundle to the cotangent bundle. And this is a Dirac structure, and closure with respect to this bracket is exactly the property that omega is a closed two-form. So more generally, I can take a Poisson structure, and then I can look at the graph of the Poisson bivector. So this is pi sharp of alpha, comma alpha, where alpha in the cotangent bundle of M. And this is also a Dirac structure, and again, closure with respect to, so Lagrangian comes from the fact that it's skew symmetric, and closure with respect to the bracket comes from the Jacobi identity now. And quasi-Poisson things also fit into this framework, but in a somewhat more complicated way that I won't say in full detail. So if I have a quasi-Poisson manifold, then the quasi-Poisson bivector also corresponds to a Dirac structure. But this Dirac structure is no longer the graph of something. It has something that looks like pi sharp of alpha plus Cm in the first coordinate and some more complicated function in the cotangent coordinate. And this runs over one forms alpha and Lie algebra element C. So here I have an action of a group G, and then this Dirac structure in the first coordinate is going to be given by sums of the form something from the image of pi sharp and something that is an action vector field from the action of G. So when I have such structures, obviously I can ask what are useful maps between them. I'll give one definition that is an example of such a map. So suppose that mu is a map from a Dirac manifold M to a Dirac manifold X. This map is going to be called Dirac if it satisfies two properties. So the first one is that the Dirac structure on X is induced by the Dirac structure on M in the following way. It consists of pairs of the form mu star applied to a vector v, comma alpha, property that v fallback of alpha is in Lm. So in other words, this bundle is the bundle of all pairs that come from pairs in the bundle sitting above M. And we should think of this, if these were both Poisson manifolds, then this condition would be exactly the condition for the bivector on M to push forward to the bivector on X, and this would be a Poisson map. And the second condition is a kind of, you can think of it as a non-degeneracy condition. It says that Lm intersects the kernel of this map transversely. So what does this mean? Just by linear algebra, this means that, here I did here, this means that for every point in Lx, there is a unique point in Lm that it comes from. So such that mu star v is equal to W. And if this is the case, then we get a Lie algebroid action of Lx on the manifold M, which just takes a point of the form mu lower star v comma alpha and maps to v. So this map is well defined because mu lower star v comes from a unique v in the Dirac structure upstairs. So what this should remind you of is what I said at the very beginning about Poisson maps into G star giving us an action of the group G on the manifold that we're mapping from. So let me say some examples. If I view the Lie algebra, the dual of the Lie algebra G star, it's a Poisson manifold, so I think of it as a Dirac manifold. And then I can ask, what are all possible Dirac maps into G star? One can prove that any Dirac map into G star is actually coming from another Poisson manifold. So these are the same thing as Poisson maps into G star. And as we saw at the beginning, Poisson maps into G star are the same thing as Hamiltonian Poisson G spaces. And similarly, if I'm interested in Dirac maps into the group G, viewed as a quasi-Poisson manifold, these are going to be in bijection with Hamiltonian quasi-Poisson G-spaces. So these Dirac maps are somehow the correct analog of moment maps in Poisson geometry and in quasi-Poisson geometry, because what they do is they kind of induce an action of what is now a Lie algebroid downstairs onto the manifold upstairs.
You mean G capital figures? The last line.
To be a bijection, I actually have to have Lie algebra G spaces, because it's possible that I have a Lie algebra acting infinitesimally on a manifold. I can still define this notion of quasi-Poisson. Maybe the action doesn't integrate, but I still have a moment map. So I was a bit sloppy in my definition. Okay, so now I can quickly say a definition, and then I can say theorem. So what we did with Maxence is that we defined a reduction level of a Dirac manifold X. And this is a pair S sub phi, S and phi, where S is a submanifold of M, X, excuse me. And phi is a map from S to some other Dirac space Z. And these two satisfy some conditions. The first kind of collection of conditions, there's some compatibility conditions on phi, which I won't state. And the second is that if I take the intersection of the Dirac structure on X, which is a vector bundle on X, I restrict it to a vector bundle on S, and then I intersect with TS plus the annihilator of the tangent bundle of S. And then I intersect further with the subbundle where the vectors come only from things in the kernel of phi. So this is, you can sort of ignore what's written here, that this intersection has constant rank.
When you say these examples, the equivalence, Dirac maps a G star, that's assuming that the source is Poisson, right?
No, no. If I have a Dirac manifold that has a Dirac map to G star, then the Dirac manifold was actually a Poisson manifold.
Has to be Poisson.
And similarly, if I have a Dirac manifold that has a Dirac map to G, then it was actually a quasi-Poisson manifold to begin with. And this Dirac map was a quasi-Poisson moment map. Okay. Sorry?
Phi in particular is regular?
What do you mean by regular? Yeah, it has a constant rank. Yes. So this is not a real definition. It's just a hand-wavy definition to give an idea of what happens. So if these conditions are satisfied, then this guy S phi, which is a priori just a vector bundle living over S, it's actually a subalgebroid of Lx. So it has an algebroid vector. And this means that it acts on things. And our theorem says if I have mu from M to X, a Dirac map, and S phi, a reduction level of the target, And I need some regularity conditions to ensure that when I take the pullback, the preimage of S through mu, I get something smooth. So I'll say that mu, S intersects mu cleanly. And the quotient of the preimage of S by the action of this algebroid exists. Then we get the following diagram. So I can take the preimage of S under mu. This is the submanifold of M. I can quotient down by the action of this Lie algebroid. And what I have kind of residually is a map going from this preimage to the manifold Z just by first applying mu and then applying phi. Because S was equipped with this constant ring. And this map descends to some phi bar. And the statement is that Q gets a Dirac structure by reduction, so I kind of pull back to this preimage and then push down to the quotient. And this phi bar is a Dirac map. So what is this bias? Well, if Z was the dual of a Lie algebra, this would tell us that the Dirac structure that I got on Q is actually a Poisson structure with a Hamiltonian action of G. If Z was the group G equipped with the quasi-Poisson structure that I gave before, then this result would tell us that Q is actually a quasi-Poisson manifold with a moment map that goes to G. And this is what happens in the examples of multiplicative Whittaker and multiplicative Mortacci-Kala that I gave, that my reduction level is, for example, one of these transversal slices. This Z is the Lie group Z that appeared there, which has a natural quasi-Poisson structure. And then applying this theorem, I just kind of automatically get this quasi-Poisson structure on these quotients of preimages of the slices in the middle. Okay, so now I'm over time, so I will stop.